Hello everybody and welcome to a very energy efficient all-electric house. My name is Rob Nicely and I'm the president of a company called Carmel Building and Design, and we're residential general contractors here in the Monterey Bay area in California. And we're here today to look at this house that's in the framing stage, which is a house that's being built in the Passive House protocol. So if you've never heard of Passive House before, Passive House is actually a German building standard, and the house in Passive House actually means building, so it's applicable to any kind of a building. So, I build houses myself, but what you're going to see here today is a single family home, but it's applicable to any kind of a building. Passive House first became a building standard in 1992, like I said, in Germany. It is a result of, in the, say, 1970s OPEC oil embargo, the beginning of people understanding that petroleum was an unlimited resource, and that we would have to, at some point, start building better buildings that used less energy to keep people comfortable. It's widely adopted around the world, but in the United States there's been very little uptake up until now. The interesting thing about Passive House is that it's based on, or there are many interesting things, but one thing that's interesting is that it's based on an energy model called the PHPP, or Passive House Planning Package. So the first thing we do is that we model the house that we're going to build in the software, so we know exactly what level of energy performance we're going to get, and how we're going to have to build the building to make sure that it runs on a very small amount of energy. So it's typical amongst people in Passive House to say that a Passive House building will operate with maybe 10% of the energy for heating and cooling, because we are really focused on trying to find ways to drive down greenhouse gas emissions and combat the climate crisis, and how we can do that in the built environment. That's why we're here today. And what we want to do is walk you through some of the special things that we do to make a house more energy efficient. To that end, we're going to be talking about mainly the building envelope, which is the boundary between inside and outside. So that's the floor, the walls, and the roof of the building, and also the mechanical systems. So a lot to talk about. I know it's going to be a little bit like drinking from the fire hose here, listening to me, but I hope you can bear with me. And yeah, let's take a look at this Passive House. Okay, so here we are, station number one. In the opening, I said that the things that we're going to talk about are going to be broadly broken into either things that have to do with the building envelope, or the barrier between inside and outside, or mechanical systems. So the first thing we're going to talk about is the windows, which is part of the boundary between inside and outside. So the windows we decided to use in this project are made by a company called Alpen, and they're triple pane windows. Over the years, there's a lot of North American manufacturers have come into this market of higher performing windows, and Alpen is one of those. Triple pane, you can see right here. Basically, you can imagine that in the world of conductivity, glass is pretty conductive, or in other words, it's easy for energy to escape through a window. So a few years ago, we went from in the old days, you would have had a single pane window. A few years ago, we went to dual pane windows, and now we have triple pane windows that are available. So these air spaces in between the panes of glass act like insulation. The still air in between the glass will actually resist the transfer of heat. So having a window that actually has 3 panes will even do a better job of that. It's interesting, you would think once you get some good glass in the window, it turns out that you get more energy transfer through the frame, which intuitively doesn't make any sense, but the whole metric changes when you start to change the components. And once the glass is good, then we have to start to think about what is the energy transfer through this part of the window. So you can see in this particular window that there's actually insulation inside the frame to resist the transmission of energy from one side to the other here. Okay, the next subject is air sealing. So this is another thermal boundary measure that we use to increase performance. When most people think about thermal performance in the building, they normally think about insulation first. And insulation is a measure to impede energy moving through the solid parts of the building, the wall, the floor, the roof. Another thing that really needs to be considered is energy that's escaping the building by going through cracks or holes. This is often between assemblies or possibly holes drilled through an assembly. And it's interesting, but we haven't really thought too much about that in the past as an industry. But it kind of makes sense that you would have energy. It's easier for energy to escape by going through a hole than by trying to go through something solid. So recently it's become part of our protocol, the way that we build houses, to start consider air sealing. So if you think of a building, any building as more or less being a six-sided box, the first thing that you have to do is you have to come up with a plan of how you're going to make sure that that thing is airtight. And the way that you do that, the first thing you're going to do is, this is sort of a section of a building. We take out the plans and you take out a red pen and you actually draw a line around the perimeter of the building that you want to be your thermal boundary. The reason you do this is because you have to consider how you're going to build these various areas to make it as easy as possible to air seal. If, for example, you wanted to air seal around all the rafter tails coming through, that's going to be pretty time consuming. But if you can figure out a way to construct the building so that you don't have to deal with all these penetrations, in other words, you might bolt on the rafter tails after you're done with your air sealing, it'll make it a lot less labor intense and a lot less expensive to do that. Once you've sort of come up with your strategy, the main thing you're going to do is you're going to start to air seal all the expanses of surface that are the boundary between inside and outside. And there's many ways to do that. We've sort of settled on using membranes to do that. So this would be an example of a membrane. This is actually what we're using on this house. And this has particular properties that are important when you're making a tighter construction. So this is designed to resist transfer of air and to properly deal with the transfer of moisture. So once you've done your first round of air sealing, you're going to want to do a test while the building is still open so you can make sure that you're close to whatever your target is. This building has been framed and the doors and windows have been installed, so we have a boundary on the outside and we can test to make sure that we're getting to the level of performance that we need to get to. In Passive House, you need to get to 0.6 air changes per hour. So that means whatever volume of air is in this building under test conditions, which is a situation where you very slightly pressurize the building to create a differential, only 0.6 of the total volume of air is leaking out of the building. By contrast, the code model is 7 air changes per hour. So you can see it's quite a bit less air movement that's required to get to the Passive House standard. As it happens, we've already done our preliminary test here. We did it a couple days ago, and we got to 0.33. So we're just about twice as tight as we need to be to hit the standard, and that's just on our first go round. So we're doing pretty good here. So this is the apparatus that we use to actually test the air tightness, and this is called a blower door. And if we were actually running a test right now, what we'd be doing is that we would put this membrane, this red rectangle, in one of the doors. We would be making sure that all the other exterior doors and windows were closed, and then this fan would be installed in the door and connected to a sensor, which was in turn connected to a computer, and we would turn this fan on, and that would create a slight pressure differential between inside and outside. And what this is meant to do is simulate the circumstances where a building might leak air. The metric is that we have to get at or below 0.6 air changes per hour. This building just tested last week at 0.33 air changes per hour. A conventional building, it's sort of all over the map, but buildings by and large are pretty leaky because in the past, we never thought about this. So we've measured buildings that were 10 or 15 air changes per hour. The state of California, the software that they use assumes 7 air changes per hour. But because air leaking out is taking with it a lot of energy, we're trying to drive it down to much less volume of air leaking. Another thing that's worth mentioning is this is primarily an energy measure, but air leaking through the building assemblies also has a significant impact on the healthfulness of the air inside. If in the example I mentioned, air is rising and the incoming air is coming from the bottom, then it's just kind of working its way in wherever it can find its way in. And that's typically going to be the crawl space, and it might be picking up dust or toxins or allergens as it's coming in. Whereas when the building is tight, and as we'll see in a minute, we're introducing air. That air is going through a filter, and it's coming in a place where we understand where it is and we understand that it's clean. Another important thing to mention here is that if air is migrating through, let's say, the walls, all air has some moisture in it, and as that air is working its way in, it might be leaving some of that moisture inside the wall. And if you ever walk into a house and you've immediately noticed sort of a musty or moldy smell, that's probably what's happening, and that is not good for the occupants, and it's certainly not good for the building, because that introduction of moisture oftentimes is going to lead to wood rot, which is what actually kills off a lot of buildings or gets them to the point where they're no longer usable. So once you have an airtight home, you have to introduce mechanical ventilation. This is something that's happened for a long time in bigger buildings, which stands to reason. If you have, say, an apartment building or an office building, and there are people that are far away from an exterior wall, or there are just a lot of people in one building, of course you have to account for making sure that there's enough air for everybody to breathe, and that air is circulating enough so everyone can be comfortable. In a smaller building, like a home, this isn't something that we've taken an active interest in the past, but as of the last code cycle, there's actually mechanical ventilation is included for new construction in California now. So it's part of the work that we have to do to provide ventilation, but per the code, so far they don't have balanced ventilation. So that means that you can just wire, say, a bathroom fan to run all the time, which means that you would be exhausting air, but if the house is really tight, it's hard for the makeup air to come in and replace that air. So hopefully we're going to get to the point soon where people are thinking in terms of a balanced system. And what a balanced system means is that if we have air exhausting out, we also have air that's being supplied to come back in, so that number one, the pressure stays stable, but also the fan that's trying to exhaust air isn't trying to overcome that pressure because there's no place for air to come from. So when you have a balanced system, it's going to work more efficiently. So that's the kind of a system we have here, a balanced ventilation system. We're using a product line called Zehnder, which at the moment is by far the best product that's out there. It's a little pricey, but it's very efficient. The fan is extremely efficient. And then the other thing in the kinds of houses that we're building that's important, the other important concept, is that this is a heat recovery ventilation system. So we've talked a lot up until now about the fact that we're trying to create a really good thermal boundary between inside and outside. Now I'm talking about pumping a whole bunch of air out of this and having a whole bunch of air come from the outside. So an important concept here is that we want as much as possible to be saving that energy and having it come in with the incoming air. So it happens that in this system, the outgoing air and the incoming air pass by one another. They don't mix, but as they pass by one another, the energy or the heat from the outgoing air is getting transferred into the incoming air. And in the Zehnder system, that transfer is about 85% efficient. So if the outgoing air is 70 degrees, and let's say the outside air, the incoming air is say 40 degrees, then because of that 85% efficiency, the air that actually makes it into the house, the new fresh air, is going to be about 65 degrees. So we're not having to put new energy to bring it all the way back up to 70. It's just 5 degrees cooler. So the majority of the energy is saved, and we're providing fresh air ventilation. Okay, now we're going to talk a little bit about the space conditioning in a house. And in a highly efficient house and in an electric house, what we use is a heat pump. Now, a heat pump is an electric appliance that, rather than producing heat, what it does is it moves heat from where it is to where you want it. And this is in contrast to a conventional heating system, which would be a combustion-based appliance and would typically have a furnace. So a furnace makes heat by burning a flammable gas, whereas a heat pump makes heat by taking the heat and moving it to where you want it. So your refrigerator, as an example, is a heat pump, and what a refrigerator does is it takes the energy or the heat from inside the refrigerator and it puts it outside in back of the refrigerator, and that's what those coils are doing on the back of your refrigerator. They're dissipating that heat. In the same way, you can use a similar system and put part of the appliance inside the house and part of it outside the house and transfer heat whichever direction you want to make either cold or heat inside your house. So in conventional construction, we would use separate systems to do those things. We would use something like a furnace to make heat inside your house, and if you're in a place where you need air conditioning, there would be a separate system that made cold in your house when you wanted that. When we're using a heat pump, we can just use one system to do both of those things. Okay, now we're going to talk about the plumbing system. And like the space conditioning, the plumbing system should also be run with a heat pump appliance. So the water heater, which in many cases in the past was a combustion appliance, was using natural gas or propane to make hot water, can now be, that hot water can now be made just like in the space heating example with a heat pump, and that's what we should be shooting for. I've done many swap outs of natural gas water heaters, and a heat pump water heater is the same size and shape. You just plug it in right where the other one was. The only difference is that if there isn't enough electricity there, you'll probably need to bring a dedicated circuit so that you have enough electricity at the appliance. That's the only difference. In California, it happens to be important that we don't waste a lot of water while we're waiting for hot water. And as a result, in the area that I live, about 15 years ago, a new rule came online where we have to use a pump on the hot water system. And the idea here is that when you turn on the hot water, we want the hot water to get hot as fast as it can. So we're wasting as little water waiting for hot water as possible. So the idea of not wasting water worked its way into the code. Another thing that happens when you're wasting water is you're probably wasting energy too. So there's a very simple strategy that we've adopted that amounts to just getting the hot. You can think of a plumbing system as being a big loop. So the water leaves the hot water heater, it goes around to all the fixtures, and then because of this pump situation, it has to pump to some place, so it pumps that back to the water heater. To save energy and save water, the best thing to do is just make sure that that big part of the plumbing system is as close to the fixtures as possible. And if you think about this, it makes sense. When you turn the hot water on at, say, your bathroom faucet, what you want to have happen is you want that hot water that's been circulated out to be as close to the faucet as possible. You want to, and so let's say that from the main line you have 6 feet left of smaller plumbing pipe to get to your faucet. The shorter that is and the smaller the pipe is, the less water is contained there, and since water flows out at some consistent rate, in our area, a faucet might be 1.8 gallons per minute, something like that. If there's a very small amount of water there, then that water will come out fast and it won't be too many seconds before you have hot water. So that's the aim there. The problem with this system when it first came online is that the last thing you want to do is make water hot and then be circulating it constantly and have that heat be leaking out basically because you're pumping it through a radiator 24 hours a day. Of course, we insulate the hot water line, and that retards the rate at which the energy is coming out, the heat's going out of the water. But we certainly don't want to be running that water through that loop. There's the energy that the pump uses and also the energy we're losing from the hot water getting colder. So what we've done is we put a sensor just in that loop, just past the last hot water fixture. So let's say that the pump turns on, the water is coming out of the hot water heater at, say, 110 degrees, and it goes around and it gets to that sensor. When the sensor reads that 110 degrees, it turns the pump off. So now there's hot water available close to all the fixtures. Because of the insulation, we'll keep the hot in there as long as we can. And the pump isn't having to run all the time to drive down the amount of water waste. Let's say now that with that amount of insulation, it takes a half an hour for the water to get down to 90 degrees or 95 degrees. And incidentally, most people don't use the water at the heat that comes out of the water heater. They mix it down by turning on some cold water. Like when you're in the shower, you don't peg it over to the full hot position. You'll come back a little bit and mix it to the temperature you want. So let's say the water gets down to that temperature, and then the system kicks on again, pump runs, and it runs again for, say, 2 minutes until the water is hot at the last fixture again. So now we're running, instead of running that pump, 60 minutes per hour, we're running at a couple minutes per hour, and we're making sure to get hot water where it belongs. Advanced framing is about is, generally speaking, the way buildings are framed relies on doing some things that are just sort of things we all learned how to do from our dads, and there are sticks in buildings or framing members in buildings that don't really serve any purpose, and we just put them in there because we've always put them in there. So the idea of advanced framing is to take a fresh look at how we frame a building and all the pieces that are in it, and whether or not they're really necessary. And the reason we're doing that is because we're trying to create the conditions, number one, where there's less framing and consequently more room for insulation, and number two, in areas where in the past we might have created voids that can't be insulated, we want to get rid of all those. So in normal construction, the way it works is you frame the house, and then after you're done with that and after you've done the wiring and plumbing, the insulator comes. And if there are places that you've put so much wood in that the insulator can't get in there to insulate, those places are going to stay voids forever. So those diminishing the amount of wood and not creating those voids are the two things that we're after when we talk about advanced framing. So anybody can do this. What you need to do is you need to have a structural engineer that understands what your objectives are and that he's willing to help you by designing the building, doing the engineering so that you can use these techniques. Now there are several techniques that we use to drive down the amount of lumber that we're using. There's things like just diminishing the amount of lumber we use to frame around windows. There's different ways we treat the corners so that they're more open and we're using less lumber. There's different ways that we deal with the partitions, which is the area where an interior wall meets an exterior wall. And we change, when possible, we change the frequency that we put the lumber in. So it's typical to use 16 inches on center. There are many times when we can go to 24 inches on center. So all these things are subsets or components of advanced framing. So the objective of doing these advanced framing techniques is to drive down the amount of lumber we're actually using to frame these different assemblies. And sort of a metric we use is that in a conventionally framed building, sort of on aggregate, you're going to have about a 25 or 30% framing factor, and that means of the area of the exterior walls, 25 or 30% of that is actually going to be filled up with wood. So what we're trying to do as a result of all these different techniques is we're trying to drive down the percentage of the exterior walls that are filled up with wood. And by employing all these techniques, it's possible to get down to maybe 15% framing factor, which is actually a third less sticks. So all that exterior space gets to be filled up with, that extra space gets to be filled up with insulation, and also we're creating less voids, so we're making sure that we're getting insulation in every little place. Now, this positively affects the thermal performance of the building, but the other thing that it does is it's quite a significant cost savings. On the certified passive houses that I've built so far, I'm finding that it's driving down the framing budget by about 20%, and that's simply because you're buying less material and you're cutting and installing less material. So that's been my experience so far. Okay, now we're going to talk about thermal bridging. So this is another one of those thermal boundary subjects. And what thermal bridging is it's about if you have a material that's highly conductive, that energy passes easily through, and that material goes from the conditioned space on the inside to the outside space, then you have a situation where energy can transfer very rapidly from inside to outside. And we've gone to lengths now to create the conditions where the whole building envelope is like a thermos, that it's very good at resisting that transfer. But now we have a condition where at one point a lot of energy can be passing through, and there's a huge difference between how conductive different kinds of materials that we use are. The most conductive is steel. So we don't use a ton of steel, but in a condition where if we had like a big span or a cantilever deck and we were obliged to use structural steel, and if that structural steel went from the conditioned space to outside, we would have a place where a lot of energy was leaking out of the house. And just to give you an idea of how different the range is, steel conducts energy 1,600 times more readily than wood. Concrete also is a good conductor of energy, so although we don't have too many times when we have concrete that is going to be going from inside the conditioned space to outside, in buildings where you do have that, again, you have to have some way to interrupt that energy transfer. So the big thing in thermal bridging is to make sure that you don't create conditions like that, because it's really going to drive up the amount of energy that you have to use to keep the building comfortable. After you've made sure that you haven't made any big mistakes like that, then we get down to smaller thermal bridges. So This image here actually shows a conventionally built house, and you can see it's a thermal image, and you can see all these lines where you can actually see the studs. And what that represents is that the energy and the heat, this is a thermal image, so we're measuring the surface temperature. These areas are slightly hotter than the adjacent areas where we have the insulation. And then you can also see in this image that the window areas, the area where there's glass, there's even more energy transferring through. So again, we've talked about how once you make the whole pie smaller, some of the things that were small slices of the pie start to look bigger. So thermal bridging is one of those areas. This house, where we have exterior insulation, so not only are we going to have insulation inside the building cavities, which is the normal place that you would find it, but we're also going to have a layer of insulation outboard of that that's actually going to be attached to the outside of the framing. This is a practice that's becoming more common in residential construction, and in the future you're going to start to see more of this. But this, in addition to just adding more R value to the assembly, the other really nice thing about this is that it creates the conditions where you have a layer of insulation that passes over all these potential thermal bridges. So this other infrared image we have here is actually a house that we built about 8 years ago, and it was a certified passive house. In this image, you can see in the walls that you can't see any differentiation. So you're not seeing any evidence of a thermal bridge where the framing members are, and that's because there's rigid insulation on the outside of the framing. Another interesting thing to notice in this image is that earlier on I said that when you bought a good window and it had good glass, that actually you'd be getting more conductivity through the frame, and this shot here actually shows that in action, because we have a warmer area where the frame of the window is than where the glass is. So the concept of insulation and R value has come up a couple times already, but I want to focus on insulation for a minute. And the thing I want to tell you guys is that there's kind of three things that we're thinking about here when we're thinking about selecting insulation. Obviously, we're looking for the right R value so that we have the right resistance to conduction of energy through the solid assemblies, which we talked about before. But so the important things with insulation: number one, you got to pick a good insulation. Number two, it has to be well installed. And this is where a lot of stuff falls down. Like bad insulation, as an example, kind of needs to be almost perfectly installed to really perform up to that R value. So if you have R13 bad insulation and it's in a building cavity like a stud bay, it needs to be touching all six sides. If there's wires or pipes going through that stud bay, it can't be munched around the pipes and wires. It has to be cut and fitted neatly around those so that it's reaching out and touching all six sides of that box that it's in. So, while bad insulation is inexpensive and it's commonly used, you really got to focus on doing a good job with installing it. On this house, we're planning on using blown-in cellulose, and one of the nice things about any blown-in product is that it's not so fussy to install. It's much easier to get a really nice full cavity when you're using a blown-in product. So we want to select a good insulation with a good R value. We want to make sure it's installed correctly. And then we want to think about what it's composed of, and if it's bringing any toxins into the building, or what is the embodied carbon footprint of that material. So there's a lot of kinds of insulation, and you may have heard of them, that are rigid foam insulation. Now there's several kinds of this, and they each have their own qualities. But those are petroleum-based products. And, there's a wide range of, there's a discussion about, how much embodied energy is there and how long it's going to take for the insulative properties in the building and the increased efficiency to sort of overcome that embodied energy. And that's a more complicated discussion for probably later in this video. But you want to be aware of that. You want to be aware of whether or not you're bringing any toxins into the building. There's such a thing as spray foam insulation, which is toxic while it's being sprayed, and then it's going to be off-gassing for a while. So that might have a health implication. So there are many things to consider when you're thinking about what kind of insulation you want to install. Here, again, we're using the cellulose insulation blown into the inside of the walls, and we're also using exterior insulation, which is a practice that's becoming more common. And there we're using a product called Gutex, which is also a wood fiber product. So we have cellulose-based insulation inside the walls and outside the walls. And this brings up the concept of carbon sequestration. So while we're talking about the carbon footprint of a lot of products here, there are some things that will sequester carbon. In other words, when the tree was alive and it was basically breathing in carbon dioxide, and that became part of the material of the wood, so it's therefore fixed and out of the air, then it's going to, if that wood doesn't get burnt or it doesn't rot, then that carbon dioxide is just going to stay in that wood, and it's not going to end up back in the air that we're breathing. So there's an implication there in terms of greenhouse gas emissions and the carbon footprint and global warming that you also need to consider. So I mentioned a little earlier that this is an all-electric house. When we love it when we have the opportunity to build a house that doesn't need a gas hookup. It's the wave of the future for sure. There are plenty of jurisdictions around the state that are looking at either moratoriums on gas hookups or some sort of way to incentivize electrification. The state has changed their messaging about energy efficiency and greenhouse gas emissions away from net zero, which was more in circulation a few years ago, towards electrification. So if you read the literature that the state's putting out, or you hear about any new program, they're going to be talking about electrification. The reason is because we've gotten to the point where the fuels that are used at the big power plants, or the mixture, the whole palette of fuels that are being used, has become green enough that the greenhouse gas emissions that are created by producing electricity is now less than what it would take, or the greenhouse gas emissions associated with natural gas or propane use in your home. And as a consequence of that, the state is encouraging electrification now. So talked a little bit earlier about the heat pumps to be used in the area of space heating and cooling and water heating. So those are appliances that we'd like to see. They're typically combustion appliances in a conventional construction, and we want to change those over to being electric-based appliances. The other thing, and this is a little bit of a harder sell for a lot of people, is getting off that gas range and hopefully moving to an induction cooktop. So a part of the reason why, people love their gas ranges, right? Because they feel like the response is so fast. If you turn up the gas, you instantly change the heat level, whereas the old-fashioned sort of electric resistance cooktop, you change the dial and it takes a while for the heat to change. The other thing about an electric resistant cooktop is that they aren't particularly efficient, whereas the new induction cooktops are very responsive, more responsive than a gas cooktop. They boil water faster if you turn the heat up, but they're also very, very efficient. So another thing about switching to electricity is that it means that we get to go away from pumping flammable gas throughout the house, and which is probably a good thing. You would, especially in the case of an earthquake, where in the past one of the big dangers would be fire, and that's largely because the lines would rupture and then they catch on fire. We'd start to have infrastructure where we wouldn't have to worry about that. So this house is going to be a net zero house, and in the built environment, the normal definition of net zero is that it produces as much power as it consumes over the course of 1 year. So in this house, as a passive house, the first step is that we are driving down the energy demand absolutely as much as we can. And then we'll make the rest of the power with a photovoltaic array, a solar array that will make the balance of the power needed to run the house. So I said a minute ago that the state has moved their messaging away from net zero towards electrification, and I'm glad about that. The using net zero as a way to message has always sort of bothered me, and the reason is that net zero does not mean carbon neutral. And a lot of times when people hear net zero, I think that they do sort of believe it means that that building or operation or whatever they're talking about is carbon zero. And it gives people an unreasonable sense of that problem has been solved or that everything's squared away there. But there are many reasons why they're not the same thing. For example, and I'll talk a little bit more about this later, what we're talking about when we talk about the energy that the building uses during its lifetime, we're talking about operational energy. So there's a whole set of impacts that we refer to as embodied energy or embodied carbon, and that's all the carbon footprint of the materials before they got here. So the carbon associated with extracting the materials out of the ground or cutting the trees down out of the forest, the shipping, the trucking, moving those materials from one place to another, and then all the energy it took to fabricate those materials into what they were going to be in their finished product. So there's a lot that goes on before they arrive here and get installed, and the normal definition of net zero does not account for that. Also, in the realm of operational energy, there are what are sort of commonly referred to as leakages in the way those things are calculated. So it's a little complicated to talk about, but there are many reasons why even a building that's making as much power as it's consuming, that will not mean necessarily that it has zero carbon footprint associated with that. A real easy example is that you're making energy during the day, and that energy is clean energy, right? From an operational standpoint, although the photovoltaic panels themselves have a carbon footprint, a embodied carbon footprint, but you're making power, but you're probably not using it all during the day. You're probably feeding it back into the system. And then later on during the day, the sun's going down and the ability of photovoltaic panels to make power is diminishing. But around that time, we get to what we call peak load. People are coming home, they're turning on their TVs and they're doing their wash and they're turning on their stove, so that the demand is actually going up while the ability of sustainable sources to make power is going down. And on aggregate, what that means here in the Western United States, the grid encompasses everything west of the Rockies. So on aggregate in that grid, the grid managers are actually firing up maybe a coal plant or some other kind of a plant to service that additional load that's coming in the evening. So when you come home and you're consuming more energy, even though you might have produced energy during the day, then you're consuming energy that does have a carbon footprint. And because there's transmission losses and a lot of you have to produce more energy from a place far away to serve your need at home. Even if you're producing the same number of kilowatt hours as what you're consuming, more energy is actually having to be produced by the system for you to get those kilowatts. And because that energy that's coming back has a carbon footprint, then your operational energy then has a carbon footprint. The end result of all this, and the reason why it's important to focus on efficiency, is because when we look at the efficiency of the energy system in the United States right now, 70% of the energy is not being consumed for any useful purpose. 70% of the energy is turning into waste energy because it doesn't make it to an end user. So another reason why thinking in terms of net zero is probably not quite the right way to think about it is because you can make anything net zero if you're providing enough energy. And therefore it sort of puts the focus on energy production, which is probably not really the right way to think about it. The thing that's left out there is efficiency, and again, Passive House is largely focused on efficiency. If you create something that works efficiently, then you're just creating a condition where you don't need to consume anything. So we already have a very inefficient energy delivery system in the United States. So to try and solve the problem by thinking of ways to produce more energy is sort of not the way to think about it. We want to think about how we can be more efficient and how we can just not need to consume first. And then whatever demand is left over, then we'll think about satisfying that demand with the cleanest possible energy source. But we need to be thinking in terms of efficiency first. Okay, we've talked about a lot of stuff and we're finally at the last station, but I appreciate you sticking with me this long, but I do want to take just a couple minutes. We have talked about embodied carbon versus operational carbon a little bit, but just want to expand on it just a bit. What I haven't said up until now is that operational carbon is something that as a system, we're pretty conversant in. We kind of know what the operational carbon is in a building, or at least we have a better handle on it than what we have on embodied carbon. Embodied carbon, like I said before, is all the carbon that is associated with everything that happens to a product or a material before it gets here. And things like steel and concrete in my world, in the world of residential construction, are the things that have been generally identified as having the highest embodied carbon. And the reason is because both steel and the cement in concrete take an extremely high level of heat to produce. So that's really where it comes from. Aluminum is also in that category, but we don't use as much aluminum as we do concrete and steel. In my case, we don't use that much steel because these are wood frame buildings, but in the industry in general, yeah, there's a lot of steel being used. So we want to, as much as possible, control the sources of that and control how much we use. In the case of concrete, we can't stop using concrete. At least I haven't figured out how to stop using it. So what we're doing right now is there are concrete mixes that include a lot of fly ash, which is an post-industrial waste product. And fly ash can be substituted for cement and drive down the amount of cement that needs to be included in concrete. And as a consequence, it really drives down the carbon footprint of that concrete. There's also other products coming online that actually use sequestered and mineralized carbon dioxide in place of cement. So there are solutions out there for concrete. Again, I don't use that much steel, so I'm not so up on how we're going to solve the steel industrial process and the need for lots of heat in steel production. But that is like everything else. I'm sure there are people working on it. So as an industry, we're just starting to get, there's just starting to be data sets and resources for understanding how much the embodied carbon in a product affects the total carbon footprint in a given building. I have talked a little bit about the modeling that we use to design a house that's going to be very energy efficient, and in the modeling we have a pretty good handle on the operational carbon, the amount of energy it's going to take to operate the building. There are starting to be data sets for embodied carbon, and we're starting to understand how to entrain that into our thinking about what the actual carbon footprint of the building is in terms of its life cycle analysis, the whole implication of that building being there. We're starting to understand that. So hopefully in the near future, we're going to be able to understand be able to quantify that in any given building a little better than we are right now. That's kind of where the industry is right now. Another thing that I'll add is that when we talk about the operational carbon, we normally think in terms of the energy used on site, but we also, with a lot of these things, they're sort of, they're in flux, or we're trying to improve the way we think about things. So I think we also need to think about, as an example, how much energy does it take to deal with the waste that's coming out of a building, like the trash hauler, sewage? How much energy does it take to provide water to the building? The whole system does, in California, a really enormous amount of energy is used just pumping water around. So those are things that normally aren't considered, as far as I can tell, in operational carbon, but we do need to start thinking about.